Hello everyone. Welcome to the problem solving session, week 3, for the NPTEL course on computational complexity. And the topics for today are space complexity. Okay, so okay, so like we saw that time is one of the resources for computation. The more time you have, the more computation you can probably do. Similarly, space is another resource that's very commonly explored. Other resources that are out there are, so time and space, these are the most common resources. Okay, and some of the other resources are random bits. Okay, then you have something called queries and so on. You can define other resources as well, but for the scope of this course, we'll be mostly focusing on the time and space. Okay, so okay, so with respect to time, the complexity classes that we have seen so far were NP, then you have P, you have EXP, okay, and then there's a polynomial hierarchy that we saw. Okay, so I mean, it's natural because you'll think of the most common functions that are out there. I mean, of course you can think of machines that take n to the n log n much time. So those you can have quasi polynomial and so on classes, but because polynomial time and exponential time, these are more natural to think of, these are more explored in that sense. But of course, you can, for any function you can think of, you can define a complexity class with respect to it. Similarly, for space as well, we'll have the counterpart. So we have something called P space and something called Logspace. So how do we define that, or simply called L? Okay, so how do we define that? This is basically, L is the class of all languages that have okay, so L is okay. Deterministic Turing machine that runs in log space. When I say log space, what we mean is this is some order log n size tape. So one interesting property about the space is that if you have log n space that you are allowed to use, okay, so this is, let's say, log n space that you are free to use throughout the computation. The interesting thing about this is that you can reuse this space. So let's say I write 0 1 0 1 1 and so on. At this point of time, I can always go back, edit this and do whatever I want within that bound, whereas the time is sort of non-reversible. So the time that you spent right now on some computation, you cannot recover it. So it's monotone in that sense, it will only keep increasing. So so this is one difference that we have between these two resources. And then you can also think of the non-deterministic counterpart of this. So similar to the P and NP here, instead of allowing the deterministic Turing machine, if I give you the power of a non-deterministic Turing machine, then the set of all languages that have a non-deterministic Turing machine computing them and run in log space, these will be naturally the NL, in the class NL. And now we can ask the same question that we had in the time world, that whether this containment is proper, whether P is equal to NP. This is the main open question that we have. Similarly, in the space world, we have this counterpart of the L versus NL question. So we don't know whether L is equal to NL. Okay, so similarly, how do we define this P space? P space is simply the set of all languages that have a deterministic Turing machine that use polynomial space. So you can also define the non-deterministic counterpart of it, which we'll call the NP space. And we can ask the same question again, whether P space is equal to NP space. So yeah, if you recall, do we know the answer to this?
Yes, yes. So according to the Savage theorem, I mean both are equivalent. Yes. So whatever we can be. So this P space is a collection of all the languages and which are decidable by the Turing machine and which runs in the polynomial time.
Polynomial space.
Polynomial space. Yes, yes.
Yes. So yeah. So we have a surprising result in the space world, which is called the famous Savage's theorem, which says that n space of f of n, when f of n is large enough, is contained in D space, can be simulated by a deterministic Turing machine which runs in f of n square space. So therefore, if f of n is a polynomial, then the square is going to be p of n square, which is still a polynomial. Okay, so therefore, by this simple application, like a simple application of this result tells us that non-deterministic p space is actually the same, equally powerful as p space, whereas this result cannot be directly applied here in the L versus NL world, because you wanted, even if you, let's say, put log n here, you're going to get log square n, and we know that log n is asymptotically smaller than log square n, so this cannot be immediately subsumed. So this is a very long standing open question, and yeah, there's a lot of research that goes on into this. Now yeah, of course, like, you can think of, why just restrict ourselves to the log space? You can think about something smaller than that, log n space or log n space. All those classes are also very well defined and studied to some extent, but we'll think about the most natural classes for now. So we'll be focusing on these two for this course.
So I have a query at this point that according to the Savage's theorem, if P space is equivalent to the NP space, uh, then but in the Savage's theorem, one additional line usually is is given that for all the values of n, problem size is greater than log n, or some then only this the equivalence of the P space and the N space would be true. I mean the the value of n should be greater than log n.
Right, yeah, yeah.
So, and moreover, just now you also said that this, even though this P space is equivalent to n P space, but however, this does not hold true for L and NL. So, can you elaborate this? I mean, why so, and why is this not correct?
Um, okay, so okay, so if you think of this f of n as log n, okay, I mean order log n, or let's say c log n, okay, and then f square of n would be some c prime log square n, okay, but I mean we have this um, asymptotics that we do, right? We can provably show that log n is little o of um, log square n, right? So if I have a non-deterministic log space machine, that gives me a deterministic machine that runs in log square n space, which is clearly larger than uh, log n.
Okay, okay,
Okay, in case of p space, what happened is, even though this was p square, it's still a polynomial.
okay, okay,
Okay, so yeah, so basically, even if this were some n to the k, the square of that would have been n to the 2k, which is still n to the sum k prime, which is still polynomial, but that doesn't go for log.
yes.
Okay, so this directly doesn't apply. Okay, and yeah, yeah, and one more class that we had uh, seen earlier was something called the complement of NP class, which is co-NP. This is another big problem, big open problem, whether P is equal to co-NP. So the picture that we had was something like this. Um, we had NP here, we had co-NP here, and P was somewhere inside, and we don't know whether this intersection of NP and co-NP is equal to P. We know it's content, but that P is content in the intersection, but we don't know whether it is proper. So whether P is equal to NP intersection co-NP, this is another big problem that we have in the time world. Okay, and so similarly you can define a a class called co okay, I mean I'll call it co-NL, because co-L does not make sense. Co-L will simply be L, because it's a deterministic Turing machine, right? You can just swap the accept and reject states and it will, yeah, you'll get the machine. So same as saying that co P is same as P, so doesn't make sense to define co P. We'll only define it with respect to the non-deterministic classes. So yeah, you can think of a counterpart where how do we define co-NL? So co-NL is the class of all those languages whose complement is in NL. Okay, similar to how we defined co-NP. And you can ask the same question whether these two are equal. Okay, and of course you can do the same thing here, co-NP space, but here you already know, right? What so how do these three classes relate? Co-NP
So all three are equivalent.
all three are equal because we know that P space is equal to NP space. So taking a complement of that would also uh, be like swapping the accept and reject it. Whereas the same thing doesn't hold here, because we don't know whether NL is equal to L. So yeah, but surprisingly we do know that NL is equal to co-NL. Okay, so okay, I mean you might have seen the proof of this in the class. I'm just drawing the picture here. Okay, and
Yes, but so can you give an example of a NL problem which is there in NL? Like say reachability is there in NL, but then an example of a problem which is there in co-NL.
okay, so any okay path complement, or I mean path complement is what you might have done, right? um,
Path complement would mean that there does not exist a path starting from the start vertex to the target
target
vertex.
vertex, yeah.
Oh, I see. Okay, all right.
Yeah, so the way actually we show that these classes are equal is by showing that path complement, which is in co-NL, has an NL algorithm. So
Okay, okay,
okay,
all right.
okay, so we will look at other examples, like very interesting examples that, so for today we will explore this small world of log space and non-deterministic log space for the next week with tutorial, which is tomorrow, right? So I think I should have announced it at the beginning. So tomorrow we'll have a session for week 4, 9 a.m. to 11 a.m. So tomorrow what we'll do is we'll look into this P space. There are very interesting and very natural problems that are out there in P space, and those are very hard.
A small issue here that the mail which we have received, and in the mail they have given the time from 10 a.m. to 12 p.m. Tomorrow.
Oh, I see.
Yes. So you please check this email once, and so I'm okay with 10 a.m. also, no issues.
Um, okay, I mean let's stick to 9 a.m. I guess.
Yes,
I'll
no,
try to find.
I have no issues, but then in the mail they have given this
Oh
time,
yeah, yeah.
10
Thanks.
a.m.
Yeah, thanks for pointing out. I mean, I think it's too late to respond now. I mean, but okay, I'll see what can be done. Okay, but we'll have it from 9 a.m. to 11 a.m. only.
Sure, sure, sure.
Okay. Yeah. So today we'll be looking into this Logspace and the non-deterministic Logspace world. Okay. So okay, before we get that, I mean it's a slight digression, but yeah, I think I'll just take 10 minutes to go back to one question that was asked earlier. So I'll bring back the context. So we had this figure where we had NP and we had P here, and we defined something called completeness, the notion of NP completeness. Okay, so what does that mean? So we say that L is NP complete if first thing is L is in NP, and second is that for all languages L prime in NP, we have a polynomial time many one reduction to L. So if this condition is what we if this condition is met, then we say that L is NP hard. Okay, so if a language is in NP as well as its NP hard, then we called it NP complete. So these were in some sense some of the hardest problems that are there in NP. Okay, and we had put some problem. The first thing that we put here was 3 SAT, circuit SAT, vertex cover, and so on. We had many problems out here. So the question that that was asked was whether there are languages that satisfy the condition 2 but do not satisfy condition 1, and of course we want a decidable language. So uh, I'll just define the language, will not maybe like get into the rigorous proof of it, because okay, so one such language is what is called okay, so the question is whether there exists a language A which is NP hard but L is not in NP. So one such example is what is called succinct 3 SAT. Have you heard of this?
No.
Okay, so this problem is defined by Ryan Williams. This was, I think, this paper came out 10 years ago. This was a very breakthrough result. So what he showed was NEXP is not contained in ACC0. So NEXP is the non-deterministic counterpart of the EXP time language. And have you heard of ACC0?
No, probably, I mean, these are related to some circuit
Circuits.
complex.
Yeah. So to motivate this result, like why this is important, so recall that the main problem that we want to solve is whether P is equal to NP. That we don't know, but by time hierarchy theorem we do know that EXP is okay. Maybe I'm jumping into it. So okay, like if you don't know what this is, it's okay, like you can ignore this part. I just want to give the picture. Okay, so we do know that EXP is strictly bigger than P. Okay, then you can define the non-deterministic counterpart of this, which is NEXP. And okay, and within P we have this L with L is the log space machine. Okay, this is what we are doing today. Within L there are even smaller classes that are defined with respect to circuits. So ACC0 is the class of languages that have circuits which have, so I'll just define this. Okay, so these have circuits with constant depth, second thing is they use AND or negation gates and mod gates. Okay, and third thing is they have unbounded fanning. So even if you don't know what any of this is or what ACC0 is, that's completely okay. You don't need to know this. What we are just the reason why this result is important is because ideally we want to separate this, but we don't know a separation between this and something uh, something much inside. So this is like the first result that we knew, which separated a much larger class from a very small class, but we didn't know how to even prove that until a very long time. So yeah, so that's why this was a very celebrated result. Also, the techniques that it introduces is very interesting, but we'll not get into any of that. The only thing that we want to know is the definition of this problem called succinct 3-sat, which is what is used in this paper. The title of the paper is this, NEXP is not contained in ACC0. Okay, so if you are interested, you can take a look at it, but even if this does not make sense, don't worry about it. Okay, so what is this problem? This problem is very similar to the 3-sat problem. Okay, but in 3-sat problem, what is the 3-sat problem? You are given as input a formula phi, which is in 3CNF form, and you want to output yes if phi is satisfiable. Okay, now what we are doing is, we are giving, instead of giving the formula phi in this 3CNF form, x1 or x2 or say x3 bar and so on, right? Instead of giving it explicitly as a formula, what I'll do is I'll give you in some encoded form. So I'll give you like a very small description of the formula. From that you're going to extract phi, but with respect to the size of the phi, this is going to be very small. That's why it's called succinct 3-sat. So how do I represent this? Okay, so how do I represent this? The input that I'm going to give you is going to be a circuit. So I'll give you a small circuit C, and what you're going to do is that you will form a truth table out of it. So these are the variables x1, x2 and so on up to xn. So I have x1, x2 up to xn, and one more column that tells you the truth value of the circuit C on that input. So for example, if I give all zeros as input here, then whether the circuit outputs is 0 or 1. So this is just the truth value. So what is the size of this truth table? Like how many entries will be there? Like the
2 raised to the power n.
2 raised to the power n. So as you can see, like from a very small circuit that I give you, you can extract a truth table that could be exponentially larger. Now what you do is, you think of this, just a second, okay? Yeah, you think of this column, which is a binary bit, binary 2 to the n bit string. So what you do is just read this column. So it's a string, okay, and the length of it is 2 to the n. And now what you do is, you think of this as your formula phi. So does it make sense when I say that think of this string as a formula phi? Because even though we are writing the formula like this is for readability, but what is actually happening is that this is given in some encoding, which is in a binary format. So this is just for the sake of convenience, but actually it is an encoding of 0 1 star. So we have fixed some encoding how we are going to do that. Okay, and based on this, so this 0 1 string corresponds to a formula phi, which could be this large in size. Okay, so is this clear, like what we are doing? So basically we have a circuit, we look at the truth table of it, look at this last column, the truth values, and think of that as an encoding of a formula phi. So instead of giving it to you directly, I'm giving you some succinct representation. And what you want to do is, same thing, check the satisfiability of phi. So if phi is satisfied,
Actually, yeah. So this thing is not clear, that how can we consider the last the output as a Boolean formula? What does it mean?
okay.
Say if yeah.
Okay, so when we defined all these problems here, no, in this, let's say any problem in general, not just NP complete. So any problem out here. So even if it's a vertex cover, okay, the input to you is a graph and a K. So it's natural to think of. So let's say I'm talking about vertex cover. and the input to me is a graph and a number k. So k you can imagine as binary. It's easy to imagine this as a binary, it's binary equivalent. But how do you imagine the graph as binary? How do you encode the graph as in a binary encoding?
So then, I don't know, but probably we would be encoding the vertices and the edges and the connectivity. I mean, using some procedure, but I'm
Exactly.
not
So
sure.
yeah, exactly. That's exactly what we are going to do. So there could be multiple ways of doing it. One way would be that we will think of this as, let's say 0 represents that there's an edge. So I can fix for myself that the first bit corresponds to the uh, vertex v1 v2 v1 v3. There's some ordering that we have already agreed upon, v1 and so on. So basically these are all the pairs, and choose 2 pairs. And when I say 0, what that means is there is no edge between v1 and v2. When I say 1, it means there's an edge. So if I just give you this, a 0 1 uh, binary string, can you construct a graph out of it, a unique graph?
Yes, yes, I can.
Okay, so similarly, if I give you a formula phi, all I have to do is we want to encode it into a boolean string. So one way to do that, or can you think of one way to do that?
Okay, so if a Boolean formula is given to me, then I'll proceed like this. Say x1 would be represented, so position wise. Say if it is 0, then it shows that x1 is in the normal form. But then how would I represent the operand XOR or not then? So for them also I would be requiring some form of the encoding. So I'll say something like if I find another one after a one, so this is not a Boolean variable. Rather, this is an OR operator kind of the thing. So right now I cannot think of a clear-cut encoding, but yes, some sort of this form of the encoding can be used so that we can clearly distinguish in between the operators and the Boolean difference.
Huh. Exactly. So one way to do that would be that, think of um, okay. So I know that there are m many clauses. Okay. So I'm going to think of this as, I'll imagine it as blocks of some length. Okay, there are m many blocks like that. Within each block, I want to tell what variables are there. It could be x1 to xn, or it could be x1 bar to xn bar. So my this length of mine is of 2n, is of length 2n, where this corresponds to whether x1 is present, whether x1 bar is present, and so on. So if x1 is present, I'll write a 1, x2 is not present, I'll write a 0, and so on. I'll do that. So this is a very this is a very wasteful encoding, because I'm wasting a lot of space. I don't need this 2n as such. I know there are only 3 clauses, but this still works. It's not it will still be polynomial sized representation. I'm just giving this one example. Of course you can do better. So what this tells you is how to read the first clause. For the second one also, think of this as telling you, after 2n length, look at the next block, and again write what are the variables that are participating in that clause. So yeah, so the length of this string will be 2n times m, where m is the number of clauses.
What
So,
about the operators or and kind of?
so because we know it's a 3 sat formula,
Oh, okay,
3
okay.
CNF sat, we already know the format.
Yes, yes, sure.
Okay, so yeah, so this is how you can think of this boolean string as your formula phi.
Yes.
Okay, and you can actually, it is an interesting exercise to try out like several other examples and think of how you will encode it. And of course we don't want any encoding, we want a efficient encoding which is polynomial sized. Okay, so question is the same, whether is this okay, Abiru? Okay, let me know, like stop me anytime if there are any questions. So if phi is satisfiable, then output a yes, otherwise I want you to say no. So this part is exactly what the SAT does. Okay, so intuitively, can you see that this is harder than SAT, or let's say at least as hard as SAT, the 3 SAT?
So since this phi is also a Boolean formula, the only thing is that it is being represented in a different format. But I think that this is as far as the hardness is concerned. So basically, I'm interested in knowing that whether the formula is satisfiable or not. That's it. So then it makes the hardness at the same level of the traditional set.
Okay, so notice that when I give you phi, okay, sorry, when I give you phi as a formula, you are allowed to run in SAT if I give you phi directly, and the size of phi is, let's say, n. Okay, the length of the input is n. Then you are allowed to run in poly of n time, right? And in this much time you want to tell me whether it is satisfiable or not. But now what happens is, when I give you succinct 3 SAT, notice that the input that I gave you was not the formula, it was a circuit. So for the same n length, which is 2 to the n here, for the same formula, the representation that I gave you was very small. So potentially the input length here for the same formula size n would be log n, so that the formula that you extract out of it is of length n. But now you want to solve the same problem, but you are not allowed to run in n time n, right? Because you are always running in polynomial time with respect to the input size, which is log n here.
This is not clear actually. So if an instance of the satisfiability is given to us, then how can we solve this in the polynomial time at the first place, right?
Okay,
And
we are not saying that we can solve it, we are saying we want to solve it, right? So the NP problem says that you are allowed to use non-determinism, but you want to
yes,
solve in poly n time.
yes, now it's okay. And for this S set, for this modified set, the input is log n. So I mean, why the input is log n? Moreover, because I view this circuitry as something similar to the space. Because probably we can work with this much small circuit. Why so? Because every circuit can be reused kind of a thing. And because this circuit can be reused, therefore for such a use, I mean such a enormously large number of the possibilities, the small circuit is working fine. So this circuitry is here is similar to the space kind of a thing. But I could not understand why this input is log n here.
Okay, so I want to compare with respect to phi, right? So for uh, the same formula size, okay, I mean, I don't know, I think okay, let's say the input to you is of size small n, the circuit is n, then the size of the formula is as large as 2 to the n,
Yes.
which is n for s, because we are comparing, right, the two situations side by side.
It's okay, but how can we, so how this 2 raised to the power small n is equal to the capital N, just because, so just because we have constructed the Boolean formula out of 2 raised to the power n number of the possibilities, so the size of the Boolean formula is 2 raised to the power n, and on the one side, so how do you consider this 2 raised to the power small n same as the value of n?
Okay, so what we are saying is, I want to compare um, how hard it is here. So okay, so I want to compare how these two perform, right? So I should be um, thinking about the same sized formula, right? So a formula of size k here, if it takes me some polynomial amount of time.
That's okay, but then even in the satisfiability problem, the problem instance is of polynomial size, right? Like say if we consider capital N is equals to the 2 raised to the power, and probably I'm missing something. So, but this capital N is should be a polynomial thing. I mean, this, if it is the size of the Boolean formula in the satisfiability problem, its value should be the polynomial one.
Hmm.
And varies in the modified set. When you write say 2 raised to the power n is equal to capital N, and this does not seems to be justifiable because here we have something which is exponentially large.
So, okay, so how do I convince you? Mm, hmm. Okay, so we want to argue that for a formula of size n, capital N, how does SAT perform and how does succinct SAT perform for the same size, right? Otherwise, the comparison wouldn't make sense.
Yes, yes,
Hmm.
right.
So therefore, I'm for for this formula to be of size capital N, the small n will have to be log of capital N. So
Right, right. Now I understood. Yes, yes,
okay,
it's clear to me. Yeah.
good. Okay, so because we want to check the performance on the same input size, so this n is actually log of capital N.
Yes.
So now notice that earlier I was allowed to run in polynomial time with respect to input size, which is capital N. So I have this much time. Now I have polynomial time with respect to the input size, which is small n, but that is going to be logarithmic with respect to capital N.
This point is not clear. So we want polynomial in terms of still. So what do we want? We want polynomial in terms of n, and something which is polynomial in terms of capital N would obviously be exponential in terms of the small n. Because you wrote 2 raised to the power n is equal to capital N, because this n is log 2n, and something which is a polynomial of n
Okay, okay.
would
So
be
slow down.
exponential for the
Can you
small n.
go back again? Sorry. What
Yes,
is the
yes. So the thing is that we are looking for the solution which is polynomial in capital N. And since polynomial in capital N, and since capital
here?
N is
Okay.
exponential of the small n, so therefore the
Okay.
polynomial of the exponential of the small n would came out to be the exponential of the small n.
Okay, so what we are saying is, whenever we think of an NP problem, you will always run in polynomial time with respect to the input size,
Right.
right? So here the input size is capital N. So you are given this much time, poly of capital N time, to solve the same satisfiability problem, the satisfiability problem on phi.
Yes. Yes.
But here, the input size with respect to capital N is log n. Or let's forget about that for now. The input size is small n. Okay.
Yes.
So I am given poly of n time, poly of small n time.
Now
I'm
I understood.
expected to
Yeah.
solve. Okay. But
Yes. Yes.
but with respect to capital N, this is actually logarithmic time. So the whole reason this is happening is because we gave a very small representation for a
Yes.
very large formula. That's why
Yes.
now you are actually solving the same problem that you were solving here, satisfiability on phi, but now you have much less time.
Uh, yes. True.
Okay, so this is intuitively why this succinct 3 sat problem is harder than NP. You would expect it to be harder than NP because you are expected to solve the same thing but in much lesser time. Okay.
Much in so we are supposed to solve this problem in lesser time of the order of log n, and that too by using a deterministic Turing machine.
Yeah, yes. For both of them, non-deterministic Turing machine.
Okay, so this time I would be requiring more powerful NTM to finish everything in the log n time. Is this so?
Yes.
Okay, okay,
Okay.
yes.
So this is intuitively the reason why succinct 3 sat you would expect it to be harder. We didn't prove it yet. We just saw intuitive reason. But in their paper they actually do show that it is actually hard for NP. Okay. So they do show that in this paper that I talked about. Okay. Succinct 3 sat. is NP hard? Okay, so recall going back to the question that we had. We wanted a language which is hard but is not in NP. Okay,
Yes,
so
yes, yes.
we did show that it is NP hard. We didn't yet show that it is it is not in NP. Okay, so how do we show that? Actually, it turns out, I mean, this is also something that's not easy to prove. It's an entire paper of proof. So this problem is actually complete for NEXP. So can you conclude from this that, can you use, like, invoke some theorem and say that this is not in NP?
So, um, I don't remember Leibniz theorem probably, but then that talks as something else. If P is not equals to NP, then there would be
Yeah.
something else. So,
So you use something called the time hierarchy theorem. You know that
okay,
NEXP is separate from NP. So yeah, actually you can, yeah, you are given strictly more amount of time, so you can actually show that this is not in NP. This is, so succinct 3 sat is one of the hardest problems of NEXP, which is separate from NP. So
but
this,
then, how can we apply time hierarchy here? Time hierarchy says something like, say, if you give me uh, time which is greater than log n amount something, then I can decide more number of the problem compared to uh, the original ones. So, how do we find such a rigid boundary in between NEXP and NP according to the time hierarchy?
mm, okay. So okay, I think okay, so what you're saying is that the time hierarchy theorem says that if you have f of n log f of n as um,
Slightly more time, and which is multiple of the log n. I mean, slightly more than n. If you give me n log n amount of the time, then probably I would be able to decide more problems compared to the original one. I mean, in order to know that you have given me more time, I would be requiring log n amount of the effort that you have given me more time, and then I would be able to decide a larger class of the problems, I guess. So that is time hierarchy. But then, how does it apply here? I mean, I could not understand.
okay, so um, okay, so mm, okay, basically if I um, okay, so if these are the two functions, I mean n log n and n square, we know that n log n is asymptotically smaller than n square.
Yes.
Okay, so what we do know is that there are languages that can be solved in n square time but not in n log n.
Yes.
Okay, now what we have here is actually much larger. So on one hand we have, let's say, np, right? So n to the c, and on the other hand we have 2 to the n to the c, n to the k. Okay, so this is actually a much wider separation, right? So n n to the c is little of 2 to the n to the c or k, whatever.
Yes.
So actually this is much larger separation gap that you have. The gap that you have between n log n and n square is just by a factor of log n, whereas the gap that you have here is actually an exponential gap. So this is
Yes.
actually a weaker application. So this would be something stronger, and this is something you would expect. Okay, if I give you exponentially more amount of time, then it's plausible that maybe there's something that you can
Yes.
yeah.
Yes.
Okay, good. So just to yeah, just to, I mean, summarize what we did in essence is that we wanted to ask whether there are languages that are out here that are NP hard but not really in this uh, class of NP. That was the question we had, and this is just one such example. and we saw this succinct 3 sat problem where the idea is that instead of giving you the explicit formula phi, we are giving you a very succinct representation, which makes the problem harder because you have lesser time now. So that's how we saw that this is actually hard for NP, although we did not see a proof, we just saw a reasoning for that. And also here, so there are a lot of things that we are hiding here because it's actually a long proof. But yeah, just the only takeaway is that okay, here is one language which satisfies this these properties.
Yes, thanks. It is clear to me. Yeah. Thank you so much.
Good. But yeah, I mean, if you're interested, like, you can check out this paper. It's a very celebrated paper. I think it's one of the biggest results of the last few decades in the area of
Yes.
complexity. Okay, so
Yes.
now, okay, that coming back to the contents of today, what we want to do today is to study this log space class. Okay, and okay, now that we've already drawn this picture, let's ask the question. Okay, we have this. Okay, we have this. Okay, I'll just make some space. Let's draw a similar picture here, but now for the space world. So the analog of NP would be NL, and the analog of P would be L. We know that L is contained in NL. Let's ask the same question: what are the hardest languages in NL? In other words, we want to define NL completeness. So how do we define NL completeness? Like, when do you say a language is NL complete?
If the language itself is the element of NL, and all those columns which are there in NL should be space-wise reducible to that language. Where the reduction should be the log space reduction instead of the polynomial time reduction, I guess.
Exactly. So we say that this is um, NL complete if first of all it is in NL, and secondly if for all A prime in NL, A prime reduces to A. But now the notion of reduction is something that we want to carefully look at, because I cannot define polynomial time reduction here. Okay, because whenever we talk about reduction, so if I define polynomial time reduction, what will happen is everything will fall into that. Everything here will fall into this class, which is not what we want. We want a notion of hardness. So for that you will have to rest. So in case of NP, we didn't define it to be reducible with respect to NP. We looked at something smaller, potentially smaller, which was P here. So similarly here also we won't define something like P or NL reducible. We will define something smaller or potentially smaller, which is L reducible, so, or log space reducible. So what do we mean by that? There's a Turing machine that uses logarithmic amount of space and takes an instance of A prime, converts it into an instance of A, such that the condition that we saw earlier, that x is in A prime if and only if phi of x is in A, this holds. So the only thing is you always want to take something smaller whenever you are defining reductions. Okay, so that's the definition. Now we'll do some quick examples. Okay, so let's say you have this language A, which is the set of all properly balanced parentheses. So can you show that it is in L?
Yes, so because I just need to keep the counters only and not the actual values. Like say in the case of the first example, so I just need to store the counters that whether I got a match for the first one or the inner one or innermost one or not. So effectively, since I would be maintaining only the counters, and to maintain the counter, I would be requiring log n amount of the space. So yes, this belongs to the N complexity class.
Good. Yeah, exactly. So the idea is that you don't actually need to store the current status. You only need the count. So whenever a parenthesis is balanced, if the number of opening brackets that is this is smaller than or equal to number of other way around, is greater than or equal to number of closed brackets, that is this, at any point of time. Okay, and at the end you want the total number of open brackets to be equal to the total number of closed brackets. So if these two conditions are satisfied, then we know that it's a balanced parenthesis. So like Goyal said, what we'll do is you simply look at the input that is given. Okay, and what we'll do is we'll start from here and keep on counting, keep on incrementing the counter whenever you encounter an open bracket. So keep a count of number of open brackets, or let me say unmatched. So what you do is, at this point the counter is 1, at this point you see one more open bracket, increment the counter, at this point you see one more open bracket, so increment the counter. But next, when you see a closed bracket, that kind of means that you have resolved one bracket. So what you do is you decrement the counter at this point. 2, when you see another one, you're going to decrement the counter again, so this becomes 1, these are balanced. And now you see one more closed bracket, so you decrement it again. So what this 0 tells you is that at this point everything is balanced. Next, you see an open bracket, so increment the counter, close bracket, decrement the counter. At the end you should see a 0. So basically whenever you see an open bracket, we are going to increment, or let's say I'll use this count is equal to count plus plus, and initially set the count to 0. And when you see a closed bracket, then we're going to decrement the count. Okay, and at the end of all this, whenever the head has reached blank or end of input, the count, check if the count is equal to 0. And yeah, and one thing to note is that because the size of the input is n, the total number of open brackets that you can possibly see at any point of time is n. I mean, even if I don't do sanity check, the total number of maximum brackets you can see is n. So which can be represented in binary using log n many bits. So you are always running in logarithmic space. So this.
Yes.
Okay, so therefore this is in L. Okay, good. So we'll just tweak the question a little bit. Instead of just this parenthesis, you now have the squared bracket also. And yeah, so basically something like this is not balanced. You want within the square brackets, you want everything inside it to be balanced.
So this time I would be requiring two counters, one for the square bracket and one for the normal one. And I have to match normal with the normal thing and square with the square one. So I need some additional amount of the space probably. But then since I am again maintaining counters only, so therefore the entire thing can be done in the log n amount of the space.
Yeah, so that's the correct idea. So idea is that maintain two counters. One is for the parenthesis, the other is for the square bracket. The other thing we want to check is within the square bracket everything should be balanced again. So there's some sort of an additive argument here that whenever you see square bracket, you're going to check inside for a smaller problem. So eventually there's some argument that will have to be done to show that eventually this still works in Logspace, but it's very similar to the previous one, so I'll skip. But yeah, that's actually the main idea, that you keep two counters. And yeah, so I'll not write the details of this, but it can be shown that this is also in log space. Okay, good.
Yes.
So okay, let's try this is the last example for L. So try this out. So you have an undirected graph G, and which need not be connected. It could be disconnected, and you want to check whether it has a simple cycle.
So cycle would mean that I should be able to traverse. It should be a closed cycle. I should be able to traverse from a vertex to the same vertex.
Hmm.
Is this the meaning of cycle here?
This is the meaning of cycle, but simple means that you should not repeat any edges again and
Oh, I
again.
see. Self loops are not allowed.
Yeah.
Okay, okay. So yeah. So if that is the case, then basically I shall look for a string. Say if n is the number of the vertices, then I just need to store. So the values would be something like 1, 4, 6, and then 1 again. Say if this is a cycle, and if I want to store this everything in the log n amount of this space, then how can I do it? So then if the cycle is of the obviously the cycle is of the finite length. So then I would be adding log thing finite number of the times.
Hmm.
And the maximum length of the cycle then could be equals to the same as the number of the vertices. So probably if there is a cycle, then if I so U cycle stands for that. Does there exist a simple cycle or not? I mean, how do we define this U cycle problem? Is this a decision class problem or what?
Yeah. It. Yeah. I mean, if so, how do we define vertex cover, for example? So, or let's say SAT for example. How did we define that? It's a set of all formulas such that phi is satisfiable. Right.
Oh,
So
I see. So here G is the collection of all the undirected graphs and which have got a simple cycle.
yeah.
So then I should be able to store the cycle in the logarithmic amount of the space, and 1461, how to store this in the logarithmic space then. So for every value I would be requiring to store log n amount of the bits. But then what if the size
Exactly.
of the cycle becomes pretty large? So in
Exactly.
that case I would be requiring n into log n amount of the space.
Hmm.
So this is problematic, but then how to
Exactly.
reduce this n
Hmm.
into the log n thing again?
Hmm.
That seems problematic.
Hmm. Okay, good. So you are exactly on the right direction, and the block that we've hit is also yeah, the correct barrier that is there. So, but let's say I simplify the problem for you and I ask you to show that it is in NL. Then how would you do that?
Oh, that would be easy because then I'll ask the non-determinism that does there exist a cycle? I mean, should I follow this path or not, or should I follow that path or not? So in that case, if my machine tells me that okay, uh, so should I jump to this vertex or not? And will this give me, will this be the part of the cycle or not? So I keep on jumping to the
Hmm.
next thing, and then I would just be storing the
Hmm.
index of that vertex,
The start
wherein
vertex.
I need to jump,
Hmm.
and that can be done in the log n amount of this.
Hmm. Good, exactly. So here the non-determinism comes very handy because I can guess the cycle. Okay, so it will tell me, okay, you start with the vertex, I'll call it u1, and then it will tell me, okay, from here you go to u2, you go to u3, and so on, and eventually it will take me to u1. And the length of this is, like you said, bounded by n. It's a simple cycle. It can be at most using n number of vertices. Now the good thing about non-determinism is that I don't need this entire cycle given to me upfront. For example, in case of satisfiability, I needed the entire assignment upfront. But the good thing here is I don't need it. I only need a local. At any point of time, I only need local information. So just tell me first from u1 to u2. So I'll start at u1, and you tell me the next case, which is u2. So what I'll do is that I'll simply check whether there is an edge. Okay, this can be done efficiently. Now I will forget that Okay, so at least this part I should remember. Sorry, so I should remember the start vertex. That's something, that's only one extra thing that I'm remembering. This can be done in login bits, because yeah, I can represent each vertex in login bits. Now I'll forget about u2, and I'll look at the next guess that you told me, which is u3. So I'll store u3, which is again log n number of bits, but I'll forget about u2. I mean check whether there is an edge and forget about it. Then I'll go to the next thing, forget about the previous thing, just check. Each time we are just checking whether there is a valid edge. At the end, when we hit u1, we are going to match whether this vertex was equal to the vertex that we started with. So basically we are just locally looking one step ahead rather than looking at the entire thing. So because of that, and because of the fact that we can reuse the space, so I could erase this and write the new information again and again. Because of this, it's possible to solve this, check this cycle in log space. So this whole thing can be done in log space because we are reusing the space. Okay, so yeah, so this certificate sort of thing that I had, some oracle that told me that this is the cycle and I was just verifying, made it easy. But now that we want to solve it in L, we don't really know this cycle. Okay, so what we'll actually do is something much simpler. So we don't need any of this. Okay, we'll use a very simple argument. Okay, so I don't know if you've heard of this. If G is an undirected graph, G has m greater than n edges, then G contains a cycle. Have you come across this result?
So if we have more number of the edges than the number of the vertices, which is so, uh, then G contains a cycle. So I have not come across this, but then this seems justifiable. If I have more number of the edges than the number of the vertices, then we might have traversed to one
One
vertex
vertex
more than once.
more than
Yeah.
once. Yeah, so this is like pigeonhole principle argument. So
Yes.
exactly,
Yes.
that's the idea. So you, proof of this can be by PHP. So now can you use this fact, um, because notice that I don't need to give you the cycle. The question is not asking you to give a cycle, it's just asking to test whether there is a cycle. So now that you know this, can you do something um, simpler here?
Oh yes. So in this case, I need to maintain say two counters, one for the number of the vertices and the other for the number of the edges. And these two counters can be would require the space logarithmic space, and then by using that statement, that fact, then we can show that there exists a cycle. Right.
Okay, so actually this statement works. I mean, in general, it's stated when G is a connected graph, but you can also show that it works for a graph that is not connected. So why is that? Let's say that I have a graph G which is not connected, then I mean disconnected. Then it will have some connected components like this, right? So is this part okay? Um,
Yes, it is clear to me, but I was thinking that in all the problems which we discussed so far are related to the counter jumping only. So does this mean that this L class and the NL class is only related to the problems wherein we do have something related to the counters or something else also?
Yeah, definitely it has something else. I mean, one example is path itself. The proof that path is in L, um, whether there is a path from S to T, uses this idea of configurations and recursions, which does not, like, it's not just counting, but it's something more than that. So there are
Okay.
complicated examples for sure. But yeah, I've just, in this case, it so happened coincidentally that all of them turned out to be based on count. But yeah, you have complex examples sitting there. Okay, so good. Okay, so okay, I'll not get into the details. It's actually very very simple from this point. So say G is disconnected, then it has some connected components. What do we mean by that? Between any two components there is no edge, but each component within itself is connected. So let's say component Ci has mi many edges and ni many vertices. So what can you say about the sum, the total the sum of these mi's?
So mi is the number of the edges?
M1 is the number of edges in C1 with n1 vertices, M2 edges, n2 vertices, and so on.
Oh, so the sum of the edges. Uh, so this mi is the sum of the edges of all the I mean
Hmm.
uh,
All the components.
so I don't remember twice. Sum of the degrees of the vertices is equal to the twice of the number of the edges. There used to be the theorem.
Yeah, okay.
Uh,
I just want, yeah, that is correct. The handshaking lemma. I just want to relate it to, let's say the graph G has m edges and n vertices. So I want to relate this with uh,
uh, okay. So then the summation of mi in this case, so since C1 is the connected one, so therefore M1 would be greater than N1. And so this entire sum will, since M1 is N1, so and if C1 is the connected one, so is this the connected one would mean that we can make a move, a strongly connected kind of the thing, wherein we can make a move from a vertex to the any other vertex, that sort of the thing. So, or what?
okay. So okay, this need not be strongly connected, okay, because the graph is given to us. So you can adversarially give me a graph which does not have strong components as such. Okay, so I think I phrased it in a very complicated way. I think the only thing I wanted to say was this. So basically there are no edges between the components. So the only edges that are out there are within the CIs. So if I
Right.
sum up those individual edges, I'll get the total number of edges in the graph.
Yes.
Okay, and similarly, if I sum up the number of vertices in each component, I'll get the total number of vertices in the graph.
Yes.
Right.
Yes.
Now, what we know, so individually we don't know whether M1 is greater than N1 or M2 is greater than N2. We don't have any such guarantee. But what we know for sure is that M is greater than N. This is what the original graph satisfies. So then there must exist a component such that the number of edges in that component is greater than the number of vertices in that component. Can you see this?
So it is not that directly visible, quite possible that mi would be greater than nj.
But we are saying for for some component this should happen. So let's say suppose not. Okay, suppose this is not the case. What that means is for all I, mi is less than equal to ni.
Yes.
So if I sum this, summation mi will be less than equal to summation ni.
Yes.
Okay, but this is nothing but m we observed
Right.
here, and this is nothing but n, this is what we observed here, which is a contradiction to the fact that, to the assumption that m was greater than n.
Yes. Yes. Yes.
Okay, so this is called an averaging argument, and this is actually very simple to see, but it's very useful in a lot of, it's very fundamental and very useful in a lot of places, and it comes up very unexpectedly. So it's a nice thing to know. Okay, so this is what is called averaging argument in general. Okay, and okay, so then because this happens, we do know that there is a cycle in some component. So now what we'll have to do is we will have to um, yeah, find out like which component. Okay, I'm sorry for what I said. Okay, so basically we don't want to give the cycle, right? We just want to show the existence.
Yes,
Yeah.
yes,
So
yes.
so the algorithm remains the same. Count the total number of edges, count the total number of vertices, and check for this condition. But we don't. Okay, this is just the proof of existence.
Right.
Okay, good. So now I think yeah, we will move to the NL and NL completeness part. Okay, so okay, just a second. Okay, I'll just quickly review. Okay, yeah,
So, so this strongly connected language is a collection of all the graphs, wherein the graph itself is strongly connected. It would mean that from a vertex, we should be able to traverse to any other vertex, and the graph is the connected one, right?
yeah,
So, and we have to show that this is NL complete, and this is NL complete would mean that first we need to show that this is the element of NL, and
exactly.
then if I can reduce that path problem to this NL path
Yeah,
reachability path connectivity problem probably was there was NL complete.
yeah,
So then we can prove this thing.
yeah.
Uh, so yes.
Okay.
So this is strongly connectedness is NL in the sense that if I have a non-deterministic machine and uh, so see how to check that whether uh, so uh, I mean if you give me a path then I can traverse that path in the reverse and then let you know that if I can move from A to B, then by following a complicated path, say from A to B, B to C, C to D, and D to E, if this certificate is given to me, then I can tell you that can I traverse from E to A back by using the logarithmic space So if you give me so how to show that a language belongs to NL? If you give me the certificate, then I should be able to verify the certificate in the logarithmic space. Is this the meaning of proving
Yes.
something as the element of NL? Okay. So if you give me a path from A to E, I can tell you whether there exists a path from E to A or not by using the logarithmic amount of the space by just storing the counts. That's it, and nothing more than that. And now if I need to show that path problem can be reduced into
Okay, okay.
this strongly connected,
Okay, wait, wait.
so
So let's resolve the first one and like the first part of it. Okay. So what we are saying is, if I give you two vertices, say U and V, you can tell me in NL whether there is a path from U to V.
yes, so I can tell
This
you
is
there is a path from
from.
A to B. Yes,
Okay.
yes, I can tell you. I can
Yeah.
tell you this thing in NL. By
Okay.
using the logarithmic space, I can tell you.
Exactly, because you can guess the path and verify, like we did earlier, like locally verify each one step at a time. But this is not enough to say that strongly connected problem is, I mean, the graph is strongly connected, because the definition says that for any pair of vertices there should be a path. So what we are doing is, if I give you a specific U and V, then checking whether path from U to V, a directed path from U to V, can be done in NL. But for the problem to be in NL, you want that for all pair of vertices UV, this check holds.
So then this can easily be done by so because there would be NC2 number of the pairs of the vertices, there would be polynomially large number of the vertices, I mean pairs to be checked, and since the space can be reused, probably so this entire thing can be done in the logarithmic space.
Exactly. So, yeah, exactly. So, what you can sort of do is you can keep some space that is reserved for U and V. So you can start off from V1, V2, and use the counters to go through all possible pairs. So for a specific value here, you can use logarithmic amount of space here and check whether there is a path. Once you are done with that, we will use our counters and change this pair to something else. For that particular pair, we'll again reuse the same space, check for it. So So we'll have to go through all and choose too many pairs, but we are basically reusing the space again and again and solving this problem essentially. So,
Yes.
okay, good. So,
And, and now what is remaining is to show that this problem is NL hard. So I have to reduce the reachability into this thing. So reachability problems. Reachability is the element of, say, reachability is NL complete.
right.
And now, so basically I have to check how many reachabilities. I have to check and polynomially a large number of the reachabilities here from a vertex to any other vertex, and moreover in both the directions. So I need to check 2 into NC2 number of the reachabilities, and since every reachability is NL complete, so this problem is at least as hard as the reachability problem is. So therefore, this problem is NL hard as well.
Okay. So, yeah. So, actually, what we are doing is a reduction from reach to strongly connected, and this has to be in log space. Okay. So, the input to the reach problem is GST, and the input to this is some G prime. Right. So what we want to make sure is that G has S to T path if and only if G prime is strongly connected. So can you think of a modification which will ensure this? Like, how do we get the definition of G prime? So this is how we do, right? Whenever, let's say I want to show that vertex cover is NP hard, I take my formula phi from, let's say I'm doing SAT to vertex cover, I take my formula phi, convert it into a graph, and ensure that, um, I mean, X is in L if and only if phi of X is in.
Uh, oh, yes, yes. So this reachability can be rephrased. An instance of the reachability can be rephrased as an instance of the strongly connected. Like say, if G has a S to T path, then I need to show that does there exist then G has T to S path or not. So if G has a T2S path as well, then G dash has at least, I mean, this should be true for all the vertices and all pair of the vertices. Then we can show that G dash is strongly connected, and since space can be reused, so this entire NC2 number of the checks can be done in the logarithmic space only. I mean to say that G has ST path. Clearly, this can be done in the logarithmic space. So I use this much space to know that whether there exists a path from S to T or not, and then I remove everything from this space,
Huh.
and then again I check that whether there exists a path from T to S or not,
But
and yeah.
But what we are doing there is that we are actually showing that it is in NL, right? That was what we did in part A basically. That we used. So here in this space, what we actually did was we checked whether we want.
It's
Yeah. So
yes,
this is
right.
showing that it is in NL, but hardness is something else, right? Hardness would mean that every other problem in NL is reducible too. So I want to show that if I could solve this, then I could solve.
Yes, yes. So basically, we have to rephrase each and every instance of the reachability into an instance of the strongly connected. Uh, but then this, I mean, reduction does not seems to be so difficult to me. But because say the strongly connected would mean that in between any pair of the vertices there should be a path in both the directions, from S to T and as well as from T to S. That's it. So if I have an instance of the reachability, so and if I want to rephrase it into an instance of the strongly connected, then I have to create two instances of the reachability, and probably that sort of.
Okay. So, okay, not, I mean, you are thinking along the right directions, but the only thing that we want to do is like, uh, so basically, when we give a reduction, we want to transform one input instance into the other input instance, right? So, um, I mean, this is fine, right? So, I want to feed which converts this to this.
Yes, and that too in the
Okay,
logarithmic amount of the space. Now
in
I
logarithmic.
understood. Yeah.
Huh. So you are actually thinking, I mean, what you're thinking is actually correct. So I'm just going to modify this graph G slightly. So let's say um, I'll call it A B. Okay, I mean this is just some arbitrary graph. I'm not. Okay, let's say this is some part of that graph G that was given to me. So if if there is a path from A to D, I somehow want to ensure that there is a path from D to A.
Yes.
Okay, so one idea is that you can sort of duplicate these vertices. So let's say I'll add some dummy vertices here. Okay, and what it replicates is that if there is an A to B edge, then there is, so this is sort of a dummy replication of B. I'll call it capital B. This is a dummy replication of C. So what it does is that it inverts all the arrows, C to B, because there's a C to D edge here. I'll have D to C edge here. So I'm just what do you say, inverting this particular path or each edge. So what this
Yes.
ensures is that whenever there is an A to D path in the original graph, I'll have a D to A path in the new graph.
Uh, yes. Yes. So yes. Yes.
So you will need more dummy vertices here. This is, so basically every edge will have to be inverted for every pair of um,
So yeah, it's like calling reachability twice only. Reachability in one way, that A to B, and then reachability in the other way, that
other
from
way.
B to B.
Exactly, but we
Yes.
will have to do this for all pairs that are there,
Yes. Yes.
and
And
still.
can this be done in the logarithmic space then?
Okay, that is a good question. So I need to prove that this can be done in logarithmic space. Okay, so again we'll use the fact that I don't need the entire information about the graph. So notice that in order to draw this edge, I only needed the information about these two vertices. So if there is an A to B edge, I'm going to draw a dummy edge in the reverse direction. So I'm just locally looking at the information that I had here and converting it back. So I didn't need to know the entire path in order to replicate it.
Yes. Yes.
So I mean it has to be written in the form of an argument, which we are not doing right now. But yeah, I mean, yeah, this can be done in Logspace because we're only locally looking at the um,
Yes.
yeah.
Yes.
Okay, good. So yeah, so the main thing is that when you want to show it is in NL, this sort of a algorithm is okay. But if you want to show it is hard, either take some hard problem and show this reduction. I mean, yeah, this function phi that will take one instance, convert it into the other, and this argument in this case it's easy to verify because of the way we construct it. But in some cases it might be very difficult to show this kind of guarantees. Okay, so mm, okay, this is yeah, this is one nice example. This might be slightly more difficult than the previous one. So it says that you are given a directed graph and check whether it contains a cycle. So this part I think we already did earlier. This part was that you guess the cycle and locally verify.
Yes.
Okay,
Yes.
so this is the more interesting part.
So how can I then reduce reachability to the cycle? And so I mean, why do we reduce reachability to the some other problem? I mean, don't we have other problems as well which we can use to reduce to the other problem?
Yeah, exactly. That is a very good question. And in fact, in this example, we are going to need something else.
Okay.
So
So, can we take help of the strongly thing then? And strongly would mean what? Uh, no, strongly will not
will
mean.
not help,
Uh,
yeah.
yes.
So actually what you need to do is take this rich problem, convert it into some intermediate problem. First show this reduction, okay, and then show this reduction. So okay, so how do we identify what is this problem, right? So let's do the obvious thing, okay? If you have to do this, what is the difficulty you are running into? Let's identify that. If I have to naively do this.
So then I need to show that if I can reach from S to T,
Hmm.
then I need to show that S to T, and then for the given T, I need to find some other T prime,
Hmm.
and that T prime, so reachability of then T to T prime, such that the reachability of T prime, one of the reachability of the T prime will lead to S only. So we should be able to come back to the original thing. So probably, or if I further simplify this, so then reachability of S to T, uh, then I need to show that reachability of T to S as well. Then there exists a cycle.
Hmm. Exactly.
Yes, and then there exists a cycle. So while proving this thing that each and every instance of this, so whenever I have say from S to T, then I have T to S as well can be done as what? So this can be done, I guess. This can be done, and this is not that difficult. But how to write this thing formally is not clear.
Okay. So, okay. So just to slowly break down the ideas that you said. So the natural idea here was that when do I say that there is a cycle in this graph? When for some S and T there is an S to T path, and also there is a T to S path. Okay. But notice that when we do a reduction, we need an if and only if condition, right? So if there are these two paths, then there is a cycle. That part is true. But is the other way around also true?
Other way down in the sense that if there is a cycle, then we should be able to. So, because I do not understand this if and only if thing. So, if I am reducing the problem A to the problem B, and last time also you said that this reduction is if and only if kind of the situation. So, what does it mean that if x is the element of A, then the f of x is the element of B, and if x is not an element of A, then the f of x is not the element of B. Is this the meaning of if and only if kind of thing here?
Exactly. Yes. Yes.
Okay. So if that is the case here, then I need to show that if I cannot reach from S to T, then there won't be any cycle. Is this the meaning? Okay, then the cycle does not exist containing a cycle. Moreover, so quite possible that I may not be able to move from S to T, but then still there might exist a
Some
cycle.
other cycle.
So how to show this then?
Huh. Exactly. So that's what I'm saying, that the reason why this is the most natural thing to try, that this is one an NL complete problem, I know. So let's try to reduce it to cycle. And this idea that you said looks fine. That okay, I'll check whether there is a path from S to T. In another invocation, I'll check whether there is a path from T to S. So if this is true, then there is a cycle. So one direction is holding. So okay, what we want is that uh, if I'll call this, I'll just write it like this: S to T and T to S. Both paths exist if and only if G prime has a cycle. This is what the reduction gives us. That a yes instance of this should translate to a yes instance of this, and the other way around. But in this case, this part is okay, that if there is an S to T path and there's a T to S path, then I have a cycle in G prime. That is okay. But in the no case, what happens is maybe there is S to T path, but there does not exist an T to S path. Okay, that does not mean that zip time does not have a cycle. That it does not have a cycle, because I mean you can think of it. Okay, maybe there is some path like this, and there is some cycle here. Okay, so there is an S to T path. Okay, there does not exist a T to S path, but there is a cycle in the graph.
Actually, this situation is very, very specific. I mean, when we have self loop.
Not necessarily, because in this case there are no self loops.
Oh, I see. So there are the vertices in between as well.
Huh. Yeah. So
Okay,
that
quite possible, quite possible.
hmm, exactly. So that's why this reduction does not work directly as it is.
Yes.
Okay, so that's why we are going to actually need to modify this reach, get to some other problem, and from here we will reduce back to cycle. So I'll tell you what that problem is and why it is natural to think of that. Okay, so which maybe one of this is easy, so I'll do the easy part first. Okay, let me think which is easy. mm, hmm. Okay, so are you familiar with directed acyclic graphs, DAGs?
Yes. I mean, which do not form a cycle.
Exactly, so you have a directed graph and there are no directed cycles, so something like, sorry, so this is still a DAG. Okay, there is a cycle, but it's not direct. If I keep following the arrows, I will never get a cycle. So,
Yes.
okay. So now the so let me define this DAG. Uh, okay, the DAG reach problem. So says that I'm given as input a graph G, a DAG G. Okay, and two vertices S and T, and output yes if um, I mean there's a directed path from S to T. Very similar to the previous one, only that now it's a DAG. Okay, so now if I tell you come up with a reduction from DAG reach to we wanted cycle, right? Yeah. So can you now think of
So this is in the DAG reach, the input is the given input and output is yes, only if we can move from S to T. But then DAG will ensure this thing that I can only reach from S to T and not from T to S.
hmm. So
Because I mean both the things cannot be simultaneously true. I mean for a DAG reach, if the output is yes, then I can move from S to T, but simultaneously it should ensure that there is no path from T to S as well. Otherwise, this will no longer be a tag.
okay,
So
so
yeah.
so yeah,
Uh,
so what we actually want to do is again this come up with a function phi that's going to take this gst and convert it into an instance g prime such that this condition meets.
So in this, I mean, probably I think that this DAG reach is making the problem more complicated because in this case, if GST is given, then I can traverse from S to T, but I cannot traverse from T to S. So this will
So
ensure that the cycle does not exist.
huh,
If S to T happens, then the cycle does not exist.
huh. So
However, if I cannot traverse from S to T, if the output is no, uh, then nothing nothing is useful.
so this is because you are thinking about the same graph. So notice that you want to come up with a different graph G prime. So it
Oh, I see,
so
I
this
see.
is
So yeah,
this is
so
very
then
similar
probably
to
I can take the inverse of the graph kind of the thing, G dash.
exactly, this is very similar to what we did here. If you replicate, if you invert all the, like, create some dummy vertices, and um, so basically it's the same idea. So if I can create a dummy, so let's say this is A, this is capital A, this is B, then this is capital B, okay, and so on. So if this were my S and T, what this ensures is that if there were a path from directed path from S to T, then in the new graph there will also be a path from T to S.
Don't actually understand this. Yeah, can you
Huh.
repeat this thing?
Hmm.
Yeah.
So this blue thing, okay, is the original graph. Hmm.
Yes.
And the nice thing about it being a DAG is that I know that if there is an S to T path, okay, in this blue graph, there cannot be a T to S path.
Yes.
Otherwise, it would have not been a DAG.
Right.
Okay, so now I'll use this to my advantage. So what I will, because I want a cycle, I want if there is an S to T path and a T to S path, then
Yes.
I'm ensured that there is a cycle. So I'm actually using the previous idea only. So what we are doing is, for every let's say I'm looking at this particular path, okay, what we will do is we will create dummy vertices now. So for this A to T edge, I'm creating a dummy vertex that, so if there's an A to T edge here in the original graph, there will be a T to A edge here in the new graph, the red one.
Okay. Okay.
And if there's a B to A edge in the original blue graph, then there's an A to B, the reverse edge.
Yes.
So
Yes.
this we will do everywhere, like we did earlier. So it will polynomially increase the size of the graph, but like we said earlier, this can be done in logarithmic space because I'm just locally looking at an edge and creating a dummy edge.
Yes.
So what this will ensure is that if there is an S to T path in the DAG G, then there has to be a T to S path in my new graph G prime,
Yes.
and hence there is a cycle in G prime. There is a
Correct.
directed cycle in G prime. This part was working here also. This was fine. That if there is S to T and T to S, then I have a cycle.
Yes.
But the problem that we ran into was because of this other direction not holding. That it may be that there is S to T path, no T to S path, but I could still have a cycle, which I was not able to detect.
Yes.
What this tag does is that it ensures that, that's the beauty of this tag, it ensures that there was no cycle inside, no directed cycle inside. That's the definition of the problem, right? the,
Yes.
okay,
Yes.
so now let's analyze what happens in the other direction. If, let's say, S to T part does not exist, or you can assume the other way around, doesn't matter. If S to T path does not exist, then in the new graph that we constructed, the dummy the appending inverted edges wala graph G prime, I cannot have a T to S path, right?
Yes. Yes.
So that would mean that you do not have a cycle.
Right.
This
But
is true
then how should,
for all
yeah.
S and T.
Yes, but then how to show that this tag reach is NL complete then? So how should I reduce then reach to normal reach to the tag reach then?
Exactly. So good. So this part is clear, right? That DAG reach
Yes.
reduces to cycle in Logspace. Now what we want to do is the first part, that reach reduces to DAG reach in Logspace. So mm, Okay, again note that I'm allowed to modify the graph. I mean, we will have to because we want to make it a DAG. So just think of it this way. I have a directed graph and I want to somehow make it a DAG. You can introduce new vertices, you can introduce new edges as long as you are doing it polynomial size blow up.
Yes. Okay. The reach. Tag would mean. Uh, okay. So this would mean that uh, whenever an age, but how to know that the inclusion of this age is going to form a cycle, right? Unless in like in the Kruskal's algorithm, we used to use the disjoint data structures kind of the thing to know whether there exists a cycle. Uh, so basically, whenever I think that by including this age, it is going to form a cycle. So instead of moving to that vertex, I will move to some vertex, a B prime kind of, then we
Exactly,
get a
it's
point.
yeah. So we will create some dummy vertices whenever you see a possibility of, I mean, basically, because you could run into cycle, what you will do is you will sort of duplicate some create some dummy vertices, so that instead of going back to the original one, I'll go back to the new one and preserve the path. So for example, let's say you have vertex A here. This is, think of this as levels now. Okay, let's say there is an edge A to B. Okay, so what I'll do is I'll think of B being a level below. I'm sort of trying to create a directed hierarchy so that I don't have to come back to A again. Hmm. So let's say then I have B to D, so I'll go back one level down, and let's say we have D to C. Okay, so okay, one second, what do I want to do? Is this enough? Okay, so okay, let me think out loud. So what I'm actually doing is, whenever you see edges, um, okay, I mean, this is a very small example, let me draw further. So let's say I had something like this. What I'm doing is I started at A. Okay, I started at A and I looked at its neighbors. Okay, so from here I'll go to its neighbor. It's like a tree computation. Now from B, if let's say from B there is a there's an edge to D. So think of, so I'll not draw something like this. Doing that might create cycle. So what I'll do is I'll duplicate uh, a new D, a dummy D, and um, yeah, draw edges here. So I'll call this dummy a D2. Okay.
But then the real problem here would be that how to know that whether the inclusion of an age is going to form a cycle. How
Whether
to know this thing? Whether by including an, I mean, this particular age, it will form a cycle. How to know this thing in advance?
no,
Uh,
so even we are not looking at whether it forms a cycle every time we will do this. So if you started at A, you look at the neighbors of A, okay, and put them in the new level. Now look at these vertices, look at their neighbors, and you are always going to put them in the next level. So you will never go back.
oh, I see.
So you are always going to duplicate.
So in that case, this entire tree is going to be converted. This entire graph is going to be converted into a tree kind of a structure, and tree is a tag.
Hmm.
Okay,
Okay.
fine, fine.
So now we need to argue that if originally there were a path from S to T, in the new graph also there will be a path. So that
So yes, that holds true. That holds true. That holds true. We would be able to traverse because we have not deleted
in
the connectivity, but we have just introduced new vertices. That's it.
exactly, and the other way around also. that if there is no S to T path, then we would not have produced any new path, because we were just following along the edges.
Yes.
Okay. Now the another thing we need to argue is that this computation can be done in log space.
This seems to be so very problematic, because if from a vertex through all the adjacent vertices, we are creating new vertices. So if there are n number of the if a path S to T has got n number of the vertices at the most, then this entire thing would be n steps steeper. And to store all these values, how much space would be requiring? Because we would just be storing counts only. So then we would be storing n number of the counts in the worst case. And at every level, again, in the worst scenario, we would again be used. Worst scenario may maintain n number of the counts. So n number of the counts horizontally, n number of the counts vertically. So this would be, say, if I need to maintain n square number of the counts in the worst situation, then how much space is required? Log n square, probably 2 log n. Yes, can be done in the logarithmic space.
Yeah. Also notice that even if this blow up were very large, I don't really need to give you the entire graph all at once or store it all at once. What logarithmic, sorry. Yeah. So what logarithmic space reductions demand is that um, if I give you an index I, okay, so this is basically, I mean, you can imagine this as a binary string. I mean, this is also a binary string, some encoding. This is also a binary string. So I don't want you to tell me this whole thing in logarithmic space. It could be larger, but what I want you is that if I tell you the ith bit of this, okay, I'll tell you an index I, you should be able to compute the value at that index 0 or 1 in logarithmic space. That's the only thing I need. So it does not mean I should give you the whole graph or store it at logarithmic value. Only the ith index should be computable in polynomial time, in logarithmic space.
Yes, yes.
Okay, so this is something that gives us more power in that sense, I mean, which we did not have for polynomial, I mean the time hierarchy per se.
Yes.
Okay, so okay, yeah, okay, so just to quickly see what we did, we actually came up with this uh, new problem called Dagrange, and yeah, we showed that it is Dagrange is NL complete, and from this we showed that cycle is also NL complete. Okay, and okay, I have two problems that are interesting. Okay, maybe we'll not get into the details of all of it. We'll quickly just discuss the ideas behind it. Okay, so yeah, so the two side problem is you are given a fee where you have yeah, I mean clauses that consist of two literals and so on, and you want to check whether this is satisfiable or not. So I think we saw this earlier, that 2 sat is in P. Okay.
Yes.
Okay. Now we are saying something stronger. We are saying that it is NL complete. So okay, I'll leave out the NL part. Um, I mean, showing that it consists of two parts. That first it is in NL, second it is NL hard. So showing that it is in NL is something you'll be. I mean, of course, you'll be able to do. So we'll look at the more interesting part, which is the hardness. So you want to take some already known NL hard problem, convert it into a 2 sat instance, or yeah, Okay, so I'll huh.
I have a related question here. That don't we have the summary of the problems or some strategy that if you give me a new problem, then I should be able to find that to which problem this problem resembles a lot, and then I should be able to consider that problem only. So don't we have some framework, and by using that framework we can find that okay, these are the key ingredients of this problem, say K, and its key ingredients are similar to the key ingredients of another problem, say M. So I should focus on only on the problem M to prove that M can be reduced, potentially, probably M can be reduced into K, and therefore K is also something which is X complete kind of the thing. Say X is the complexity class. So for a complexity class, don't we have such a framework wherein we can extract the key ingredients or the key elements of the new problems?
Okay, so um, actually, okay, the thing is, I mean, I don't know how to convince you exactly, but here is one argument why such a thing should not be possible. Because let's go back to the NP world, where um, let's say um, we had some problems that we knew are NP complete, for example 3 sat vertex cover and so on. So like we said that primality was one question. Okay, I'll just draw that diagram again. So we had some NP complete problems here and we had some P problems here, and we said that primes was a primality testing was one problem that we did not know whether, I mean, whether it's hard or whether it's going to be in P, and nothing was certain, and we kept on trying, and eventually it so happened that it went into this. Now similarly there are other problems, the minimum circuit size problem, the graph isomorphism problem, and several others which we call the NP intermediate problems, which we don't know whether they're going to fall here or whether they're going to fall here. So now if such a framework existed, then wouldn't it, I mean, wouldn't it imply that, I mean, all this like sort of things that we are trying out for such a long time to see whether, where it falls, um, I mean, that would have been like a one step answer, right? If such a framework existed, we wouldn't have kept trying. So I mean, I don't know how to convince you, but um, I'm just um, yeah, I'm just saying that I don't think such a framework um, exists, because that would actually um, um, I mean, resolve a lot of open questions that we have, right? Whether something is hard or not, that would like instantly tell you, okay, it has these properties which are close to something that we already know. So, okay, maybe it's hard already. So we would have actually ended up classifying everything, and we would not be in this gray zone.
Yes, and because I'm asking this question, that probably we can think of something similar to the Oracle Turing machine kind of a thing. That as if there is a key ingredients identification Turing machine, and whenever we submit a problem to it, the Turing machine will identify, okay, these are the key ingredients of this problem, and these ingredients matches with another problem of this complexity class, and so that are more similar, and then we can try, I mean, finding it out, right? Because like in this case you asked this question that which problem can easily be reduced into the two set, that to the logarithmic space. So I'm using my wisdom, and definitely I would be carrying out some reasoning in my mind, and the reasoning would be again to identify something which is similar to the two set. So I would be looking into the ingredients of the two set and the ingredients of that problem, and so that I can easily carry out the transformation. So this mental process probably can this be automated, or can it be something I mean formalized to I mean make this reduction process easier? Because whenever someone asks me to prove that a problem is NP complete, so for me getting a similar problem which can be translated into this problem itself seems to be as difficult as solving uh, NP complete problem itself.
Yeah, so Okay, so to answer whether it can be automated, okay, I cannot prove it cannot be, but I mean, we all believe it cannot be because, I mean, okay, I mean, I don't know how to translate it exactly, but it would be very bizarre. And to answer the how do we come up with it, every time you come up with a new problem, how do you know whether a reduction, I mean, from what problem, what is the right problem to reduce it from? So actually there is no easy answer to it because I mean, all these things that we saw right now are not something that were like, that that just tried someone immediately. People have tried these things for a very long time, and some of these we could come up with. And of course, now that we know this, okay, this is the right reduction, it's easy. What we are sort of doing is like verifying the reductions, okay, but uh, I mean, I'm pretty sure it would have been a very long process getting to it, like getting to the right problem. And I think like you develop the intuition, like the more you work on it, the more intuition you develop. But one thing is that what always works is that you try to do the most obvious thing. For example, if I were to tell you that I mean, let's say I give you this problem and I tell you that what you do is you do first you reduce this to this problem and from here you go here, then you would feel, oh, why, I mean, where did this diagram even come from? But notice that like it was not a very magical thing. What we did here was was an entire journey. What we did was, okay, let me try this problem and see where it fails. Now because it fails, we are looking at it closely and trying to see what modification can be done to yeah, to sort of make this thing work. Now that this thing works, it's not necessary that this thing should have worked. Okay, so it's a lot of trial and error that is involved, for sure. um, but I think the way you come to it is through this trial and error, like trying out the obvious things, sometimes even guessing, okay, just see whether this works. Sometimes it works, sometimes it doesn't. So okay, basically what I'm trying to say is that these reductions are not easy to come up with. And
Oh, yeah, yeah.
okay, and we do not know such a such a method. It's just something you develop the intuition if you work more on it, or you keep trying and looking at the problem more and more closely. But yeah, I mean, and that is the reason why we do not know the status of these problems, because we couldn't find something close to this. So
Okay,
yeah.
okay. Thanks. Yeah.
Okay, so good. Okay, so let's get back to this question. Um, yeah, if you recall, we had seen an algorithm why 2 sat is in P. What was the algorithm? We said that we'll look at what is called the implication graph. We know that if A implies B, this is equivalent to A bar or B. And this is equivalent to A or B bar. These are the logical equivalences. So,
Yes.
so from here I can come up with an implication graph. So if you have the vertices are x1 to xn and x1 bar to xn bar. So whenever you see this, we are going to draw those edges, two edges per clause. So then we said that if that phi is satisfiable if and only if there exists an I that does not exist an I such that xi to x, I mean, there's a cycle at xi, right? Is that what we said? there does not exist an I such that there is a path from xi to xi bar, because that would mean that at one point you are saying that xi should be true, on the other hand you are saying that xi should be false. So
Yes, it's a contradiction. Yeah.
yeah, so this is nothing but a reachability test, right,
Yes.
in a directed graph. So that's the only thing that's there to observe. So assuming you're convinced that this is true, the only thing we need to do is use the reachability test here, which we know is NL complete.
Yes.
Okay, and so it was just a quick observation. Similarly, this circuit SAT problem. Okay, so just to recall, we saw the Cook-Levin theorem, which says that for all NP complete and for all problems in NP, A reduces in polynomial time to circuit SAT. And we saw how to come up with this circuit. So the main idea was that because it's an NP machine, there exists a y polynomial in length for all x such that b of xy accepts whenever x is in the language. So this is the verifier based definition, that there is a small witness which will make our deterministic Turing machine accept. So the idea here was that you have this input x and the witness y on your tape, input tape, okay, and we want to build this B. So the idea was basically that if you look at any three is that in the next step what I'm going to write in this particular, the second cell for example, only depends on what I saw. So okay, why am I writing here? Because either I was here and I moved to the right, or sorry, what am I saying? Okay, so either I was here and I chose to go to the left. So sorry, what am I saying? Okay, good. Okay, so either I was here and I wrote something and I moved to the right, or I didn't change the cell at all, didn't change the content, or I wrote something here and I moved to the, so basically it's just the left and right transitions that I have which could change the contents of the cell. So locally the content of this this particular cell only depend on the three previous three cells, okay, because we either moved to the left or right or didn't change it at all. This happens for all of them, right? So this was the construction idea. So you keep on doing this every time. So this is true for all of them, and the idea was that I can implement each of this using a circuit. So think of this as so if the tape alphabet is of size k, then think of this as log k, this is log k bits, this is log k bits, and this is log k bits. So this is a function that takes 3 log k bits and gives me what I should write here, which is again log k bits. So this particular function can be computed can be computed by a circuit. That was the idea that showed that okay, every NP problem can be converted into an instance of circuit SAT problem, which is how we got that circuit. Okay, now we are doing something further. We are actually noticing that this can be done. We saw this conversion can be done in polynomial time. We are observing something stronger, that in fact it can be done in log space time, log space. So if this picture is clear, can you see Can you see why this can be done in logarithmic space?
So actually, this CKG set, this transformation is not clear. I mean, what this CKG circuit satisfiability stands for, and how does it differ from the traditional satisfiability? And one thing I can observe here is that since this is the circuitry version of the problem, so definitely lot many things can be given as an input. And then we would be requiring the limited amount of the circuitry to produce the result. Something similar to the succinct set problem we already discussed. So, I mean, like in this problem also, without understanding much what the formulation of the CKT set is, I can make it out that we would be requiring a very limited number of the connections in the circuitry to come up with something, and that may require the logarithmic amount of the space.
Okay. Okay. So, um, okay. Mm, okay. So let me start by um, saying that. So you know that you had this figure where we had this all NP problems, and we said that the circuit SAT was the first NP complete problem. Hmm. This.
I thought that CNF satisfiability was the first problem, and which was no, which was proved as anti-complete in the Cook-Levin theorem.
Mm, okay, so circuit SAT is actually a more general problem. It just says that it should be a circuit, whereas the CNF says that it should be a CNF. Okay, so the original Cook-Levin construction, as far as I remember, it it actually gives you a circuit, but you can process it few levels down and say that actually you can convert it into a CNF. So CNFs are just special forms of circuits, right?
Okay,
Hmm.
okay.
So I think the original reduction that was shown was just the circuit SAT version, which is the most general version. So it being CNF only adds to its properties.
Because in most of the proofs, they considered that the CNF set was proved as NP complete,
So,
and then they draw that tableau kind of the thing. Even in the lectures in this course, they draw a tableau,
tableau, yeah.
and finally concluded that every algorithm is basically a Boolean, can be encoded as a Boolean formula kind of thing.
Yeah, so actually these are two different proofs of the same thing. So one is through the tableau, that will directly give you a CNF, whereas I kind of personally prefer this version because it is more natural. To me it appeals. It appeals more naturally to me because okay. So maybe I'll just try to um, explain this quickly. So okay, so this part is clear, right? That I have my input x and y, the guess file. And what I want to do is, we want to accept if, um, I mean, so if x is in language, there will be a y which will make p of x y accept. That is the definition that we are working with. So this is the verifier definition.
Yes,
Hmm.
yes.
Okay, so what we want to do in order to show that every A in NP reduces to the circuit SAT problem is that I want to simulate the working of B, which is a Turing machine, a deterministic Turing machine, with the circuit, such that whenever B of xy accepts, my circuit should be satisfiable. Whenever B of xy rejects, my circuit should not be satisfiable.
Okay.
So actually what we are doing is very intuitive. Basically we are simulating every step of the Turing machine B. Okay, so let's say this is the original content, x followed by y, that is what we have. Now head is here at the moment, and what happens next is depends on the transition function. So if the transition function says that you are at the start state and this is the particular symbol B that we are reading. What else do we need? That's all, right? Then it will tell me which state to go to, whether to and what to write there. So I'll call it B tilde, and whether to go to the left or right.
Yes.
Okay, and we are looking at the deterministic version because B is a deterministic machine, so I only have one choice.
Yes.
So yeah, so so what I'm writing here, this is the starting configuration, and this thing is what happens one step after the run off machine. So basically I'm just modifying writing the next configurations here. Okay.
Okay.
Okay, so if I wrote something here on the second cell, okay, I mean if I'm currently at the second cell, that could have been because I was earlier in the first cell and the transition told me to go to the right. That is how I could end up in the second cell. Or it could be that I was in the third cell and the transition told me to go to the left.
Yes. Right.
And we're not right now having the stay option. Stay just says that you stay there, which can be implemented by going one step left and one step right. But
Right.
but the reason why we care about why this middle thing is also affecting the configuration is because it tells you what was here. So if I had a 0 here, then I'm going to retain that, I mean unless I write there. So the content of this cell determines the content of this cell.
Yes.
Okay, so basically if I need any information about this, what state it is in, if the head is there, what content it has, okay, depends only on whether if I was here, what did I read and what the transition told me, and similarly same thing for here. And if I don't write anything else, then I'm just going to copy the previous, I mean if we're not changing the content, then it's going to be the same as what it was earlier, which is what this cell tells.
Yes.
So any information about this cell only depends on these 3 bits.
Yes.
Okay, and when we define the Turing machine model, we have a more general definition where we have a tape alphabet gamma. So instead of allowing only 0, 1 values, you allow it to be some gamma mini symbols. Right. So
Yes.
So if these were just binary values, then it's very clear that what my function does is that I can write a table. If my cell, I'll call it cell 1, cell 2, cell 3 for now. If my cell 1 has 0, cell 2 has 1, there are 8 possibilities essentially, right? Then what I'll do is I'll just look at my transition table and tell you the information about this cell, because I have the values with me.
So what is C1, C2 and C3 here is?
I'll call this C1 for now, C2 for now, and C3 for now.
Yes, then it's fine.
That's
You'll
the
be
content
deciding Then based on these 3 values, we will be deciding the value of the second cell.
Based on these 3 values, and of course I know what state it was in.
Yes.
Okay, so I can directly write a function like this. I mean, if you give me some truth table, I can write a CNF form.
Yes. Yes.
Okay, but the reason why it is slightly more complicated is because I can have, in the most general definition of Turing machine, I can allow you a tape alphabet which is some constant size k rather than just ping 0, 1.
Right.
Okay, so what that would mean is C1 is not just 0 or 1, it is actually log k bits, because for k size.
Yes.
Okay, and C2 could also be log k bits, and C3 could also be log k bits. Those 3 bits will tell you what this value will be, which is again a tape alphabet. So that can also be represented by log k bits.
Yes.
Okay, so what that means is actually we are forming, instead of this just one CNF that was out there, what we are actually doing is we are looking at log k, log k, log k, 3 log k inputs and producing log k outputs. So I'll call it y1, y2 up to y log k, where each of them is actually a function like this. You can think of those as log k many single output functions.
Yes. Yes.
And each of them can actually be represented by a CNF, by the same idea.
Right.
So it's just that I mean you can still do it, but we just need to take slightly more care, but the factor is only log k here. Okay,
Correct.
so this is what happens in the second step. So for every cell here, you locally look at the neighborhood of size 3 in the previous one, and each cell here is actually just going to be like that. So you can imagine, right, these are all small circuits here.
Yes.
That from this I can tell you what is this, and I only use circuits to go from here to here.
Yes.
Okay, now same thing happens at the next level. If I want to know what happened 2 steps after running the Turing machine, same thing happens. Uh, I mean the information about this cell again only locally depends on the 3 previous cells that we had.
Yes.
Okay, so you can again think of these as lot of circuits like this. Okay, and because my machine B is a polynomial time machine, at the end of some n to the k polynomial many states, I mean configurations, I would have decided whether to accept or reject.
Yes.
So that is the main idea. So actually what we are doing is we are just looking at the simulation of B in the Turing machine world and mimicking that with circuits. Okay, so at the end, if B accepts, okay, then you're going to make sure that at the end I output a 1. My whole
Right.
circuit, which consists of all these small circuits, sub-circuits inside, and if this rejects, then I have to say 0. So this is uh, the idea behind the Cook-Levin reduction. So I mean the other version that was done in class is also can also be equivalently thought of that, but for some reason this is more intuitive to me personally. Okay, so now we know that this can be done in polynomial time.
Yes.
What we want to observe is further that this can be done in log space.
So yeah. So for I mean, one triangle is information. To maintain one triangle is sufficient. To traverse, I mean, one tape. So then there would be a polynomial number of such triangles I would require. So like say for this entire tape in the bottom, I require and for the above, I mean for this above tape as well, I would be requiring just one triangle is sufficient. So I would be requiring polynomial number of the triangles, and for every triangle I require log amount of the space. So then I would be requiring this log amount of the space how many times? Polynomial number of the times. So polynomial into log will came out to be something polynomial and probably not log space. Probably not log space.
Okay, so hmm. Okay, so actually to address the last point that you have to do it in Logspace. Again, recall that I don't want to do the entire thing in Logspace, but again, the idea is if I give you a particular index I should be able to tell you the content of that I in Logspace. So this is the same point that we discussed earlier somewhere, right?
Yes, yes, you discuss this thing, but then here in this case, I need to know the configuration that I mean in this process of
Exactly.
accepting the things,
Hmm.
what that configuration was.
Exactly. So if I ask you at some level, these were the levels, like level 0, level 1, this is how we went. If I ask you much above, my I that I give you is like way up in the level, then I need 3 previous cells. But in order to find this, I needed 3 previous cells and so on. Right? Ultimately, the only thing I have is what was given to me as input. I'm not
Yeah,
remembering all of this. Okay, so one problem that could happen here is that this is like exponentially expanding. Like this depends on 3, this depends on the other 3, and so on.
right.
Okay, so it's just about a careful analysis that you can actually reuse the space. So, how do we do that? So, this is a very nice idea that actually what you need to do is okay, let's say for now that this is my how many levels down. Okay, I'll draw one more level. And I'll label these, let's say this is sorry, a1, a2, a3, a4 and so on. Then these are my b1, b2, b3 and so on. Okay, so the nice idea here is that let's say I want to compute, I mean, of course this is a chain, right? I want this there, so for that I need this, so there's a dependency that follows. So you are sort of always going to need what's at the bottom and keep building upward. So if I want to find b1, I only need a1, a2, a3. So I will remember a1, a2, a3 and I will compute b1. Okay, so how much space did I use right now? I remembered these 3 and I'm remembering b1, so I'm using 4 whatever, I mean log, 4 times
Yeah,
log. Okay,
yeah,
now if I want to find out b2, I actually don't really need a1 at all, because b2 depends on a2, a3 and a4. hmm.
oh yes, in this way the space can be reused, right.
Exactly, so now you get b2, you don't need a2, use a5 to get b3. Now once you have these, you really don't need these. So yeah, it's basically like that. So at any point you are actually only going to need 4 or 5 of them to be remembered.
Yeah, yeah, yeah,
And once you have the values here, you really don't care about the level below.
right.
So yeah, so that's one nice idea that shows that you can therefore do it in Logspace, because you only need to remember few of them. So yeah, but
Yes.
like okay, I mean what we discuss is like sort of very high level thing, but try to formalize it. That will like, I mean, lead to more observations. So yeah, I think yeah, we'll wind up with that. So what we saw was some reductions, NL complete languages, and how to show something is in L or NL. Okay. Yeah, and tomorrow we will meet at 9 a.m. Okay. So
And which topics shall be covered in tomorrow's session and then on Monday's session?
so tomorrow is we will do P space, um, some games, interesting games that are there. So it will be entirely about P space. The next week I'm not sure what are the contents. I think time hierarchy, but I'm not sure what is being covered on the Monday week.
Okay, okay, okay.
Okay. So yeah, thank you. So I'll stop recording.
Thank you so very much, and please share notes.